So thanks for coming. I think it's the first time we have it here, and we have been promised a much more conference-like room. It's my pleasure to introduce Dr. Sonja Glavaski, who is the Program Director with ARPA-E, overseeing a portfolio of projects developing innovative and disruptive technologies focused on energy efficiency, more efficient renewable power generation, electricity grid to be more responsive to and more to disruptions and to be more resilient. Her research focuses on data analytics, distributed control, systems engineering. She was presenting something extremely interesting on electric aircraft in the ARPA-E summit.
I have that too if you give me time.
Yeah, she can definitely do that too. That was all about requirements and understanding what that system would look like and what are the gaps, technology gaps to address these types of challenges. Before ARPA-E, Sonja was with UTRC, working with Systems Controls Group.
Managing the controls.
Managing the Systems Controls Group. And before that, she was with Honeywell. She got her PhD from with Richard Murray's group, and her focus and research expertise are really in controls, analytics, systems engineering, cyber-physical systems. She will be discussing about the grid of the future. We had a very brief discussion about what that looks like, so I'm really interested in looking and attending the presentation and learning more about what ARPA-E thinks about it. So thank you very much for being here, and thank you all for being here as well.
Thank you for inviting me. And I just want to correct that actually the person who paid for my PhD is John Doyle. He's my official advisor. I did work with Richard Murray a lot at Caltech, but John is advisor and Richard Murray was co-advisor. I am very familiar with UTC and UTRC, so I'm not sure who's on camera. I do want to say that my first encounter with UConn was way back when I was doing my own master's thesis, and I was reading papers of Professor Bar Shalom on estimation and target tracking. So it's interesting how things go in circle. So given that I have limited time, I have a lot to talk about grid. I'll try to not go too fast because I want to let you be able to ask some questions. So first, I'll tell a little bit about my agency because we are learning that quite a few people do not know who we are and what our task is and what our impact is. And then I'll talk about how's US power grid looking today, what we aspire it to be, what are some drivers for the change, and some of the studies that we've done in the agency and then the program that is focusing on this that I'm running. So ARPA-E, for those of you who do not know, stands for Advanced Research Program Agency. We are made basically after the ARPA model, except that Academy of Sciences, National Academy of Sciences has recommended Congress in 2007 to establish the equivalent organization as a part of Department of Energy. And with American Compete Act, actually American Recovery Act, first funds were put in 2009. So we've been in existence for about 8 active years. And this graph just shows you how many cumulative number of awards have been announced in dark orange circle, and white circles are showing you the so-called focus programs that we have. Good news for us is that our fiscal year 2018 budget has just been announced and approved, and we got actually more than we asked for, so we have 350 million for 2018. We have 3 very clearly defined goals. If you go online and look for congressional approval of ARPA-E, we basically need to fund high-risk, high-impact technologies that will affect these 3 areas, which are improving energy efficiency, reducing emissions, and reducing import. And you can interpret these 3 goals in different ways. Reduction of import specifically is related to U.S. as a security, but when we are doing all this, we are trying to actually advance U.S. state of technology and assure that we do stay as a nation at the top of the game. We have 2 types of funding opportunities, a little bit different than other agencies. So we don't get assigned budget for each one of us that we can at our discretion distribute. We have so-called focus programs where we hire people like myself for term positions, and then we go in and define what the white space is and what are the technologies that we think would make sense for government to fund, to accelerate bringing them to market faster. And then every third year we do open solicitation. Right now we are in the midst of 2018 open solicitation. So if you have any specific questions about your submission, I am not allowed to answer to that one. So please don't ask me those questions. But that is our catch-all opportunity where we actually let people tell us what we are missing and what are the emerging areas we should be putting funding. We do have multiple areas that we've been technologies into. I don't know. Okay. It doesn't show on this. I'll have to walk, but then I'll mess that camera. So basically, I'm showing 3 bins of technologies: electricity generation and delivery, efficiency and transportation. And at the bottom, you have programs our programs are 3 years in length, and these are the programs that have ended. And on top, you see the active programs. The reason why I joined agency is because I was utterly frustrated with the lack of system-focused programs. Agency was very, very much looking into device-level technologies. And in GRID, the only program that was in existence was Genie. I did submit to that program. I didn't get funding, but then I decided to go on the other side of the table and then grab 50, 60 million and decide what we do with them. So I started a notes program that I will be talking to you about a little bit more. And then I'm very proud that, we actually as agency are getting more and more into systems, both in transportation like Transnet and XCar. We have this grid data program that is looking into creating synthetic models for the grid optimization and control technologies validation. So I think agency is thinking more broader, which I hope will continue. And I'll tell you at the end that very heavily depends on who are current program directors, because they drive the mission of the agency.
So the program directors cut across the programs, or every different column has a different group of people?
No, there's no. This is just how they're binned for the presentation purposes. But you can do. I've been telling that we should do electric aircraft for 3 years. So I'm not just in vogue, I knew that this should be done, but this was the first year that I was listened to. And that's what allowed me to get a pitch at the ARPA-E summit. So our motto as agencies, if it works, will it matter? Because I told you, we try to de-risk technologies that even private VCs wouldn't touch and then hand it over to another source of funding to get it faster to the market. And people do ask us to some extent unfairly what's the impact that we created. I'm sure you've heard all the debates about our funding and why do we need ARPA-E and all that. So in effort to show so far in these 8 years what we managed to do is on top of 1.8 billion that we as agency invested, portion of our portfolio received 2.6 billion follow-up funding, either from private sources or other government agencies. More than 70 startups have been launched from our project, and we work closely with other parts of the government. So if some of technology really needs more nurturing from government funding, then we help them find the sources. So for us, 3-pronged success is either technology that is ready to be licensed, startup, or next level of funding. All that being said, I'll switch gears and go to what keeps me busy at ARPA-E. So when we talk, and I apologize, I know there are people in the room who know GRID really well, but I'm not sure who else is in the room, so I'll start gently. So U.S. power grid has been established in early 20th century, and this chart has been put together by so-called grid tech team, basically all experts within DOE, all offices who work in the grid or related areas like vehicle to grid, building to grid. So initially, we put a grid together to make sure that energy is accessible to the citizens, that is delivered in the same manner, it's affordable. And as things happen, in the 60s, we had some blackouts. That's when we started worrying about reliability. Then there was oil embargo that made us think about more clean sources of energy. And what occupies us in the 21st century is keeping grid more resilient, more secure, and tapping into flexibility sources that are already there. So I would say that I will focus mainly on these two bubbles, flexibility and resiliency, and how do we deal with them. But first, why is grid changing? Consumers want renewables, no matter what the government policy is. These are renewable portfolio standards by each state in the United States. So on average, these 29 states that have renewable portfolio standards are asking for 20 to 30% renewable energy by, let's say, 2030. And some of the states are leading the pack. They have more aggressive goals. So California wants to be 50% renewable by 2030. So they have opened markets for distributed energy resources, and distributed energy resources are technologies that we are connecting at a low voltage levels, a distribution like storage, flexible loads, and solar generation. New York is very concerned about resiliency, so they have this New York Reforming Energy Vision where they're going to more non-wire-based solutions, more microgrids, more, again, use of DRs as opposed to rebuilding infrastructure. Hawaii, electricity is 3 times more expensive there because it's diesel-driven and you have to bring diesel to Hawaii, so that brings the cost. So these are all drivers that are there, regardless of what the big overall policy is. On top of that, we have large corporations that want to run their business in sustainable fashion. They're directly procuring renewables, and they have met 2 years ago and did some agreements on what each one of them wants to do. But to make long story short, if 1,000 world largest companies just use 10%, use 100% renewables, then they will decarbonize 10% of all electricity used worldwide. So we don't need too much to make an impact. And all this is causing the US grid to change. So current grid structure is that we, at high voltage level, produce what's called bulk power, the big power plants, and then we bring it to, transport it at high voltage levels because losses are smaller than, and then we step it down and bring it to distribution station to end user at the distribution level. So technologies that are also being introduced in this grid are distributed energy resources that I mentioned, then smart responsive loads, all the smart appliances, for example, smart homes. And then what is this causing is that this nice separate high voltage, low voltage is diminishing. And people in power systems call that diminishing transmission distribution boundary. And that brings a complexity to management of the system. And we are more concerned about flexibility and resiliency. And these technologies are actually entering at all levels of the grid. So it's not just something that is happening at the edge, but is entering at all levels of power distribution. And traditional power systems people would prefer DRs not to be around. But as consumers want them, they have to deal with them. And Siemens in 2017 actually did an audit of 200 utilities and wanted to hear from them. How do they see DRs? Are they helping? Are they not helping? And even though initially utilities were installing these technologies like distributed solar, for example, because consumers wanted and because they were improving energy efficiency, it turns out that all these devices can help us with improving resilience and reliability. And if you look on the right-hand side on the chart, what is the deployment status of some of these technologies? Energy efficiency is pretty mature. Solar is increasingly being deployed, demand response as well, but things that are on the bottom, like microgrids, combined heat and power, storage, electric vehicles, these are still in relatively early stages of deployment and integration with the grid. So how will grid of the future look like? Thinking of all these different technologies being deployed, for the lack of better terminology and not calling it Internet of Power, we say that grid of the future will look like a cheap power superhighway. It shouldn't matter where power is produced. It just has to be delivered to a user that needs it. And some of the characteristics that we don't have right now, it will have to be supported by plug-and-play architecture. It will have to have more real-time adaptation. It will should leverage DRs that are integrated, and if we do this in the way it's supposed to be done, and we will, as the end result, have reduction in CO2 footprint, which is very important. So why are we all stuck in talking about renewables and grid integration? What's the big deal? Right now, grid looks like this. We have bulk power plants that are either renewable or non-renewable. Dispatchable means that you can basically send power. You can have them produce more or less power. Most of renewable power plants, we don't have control. So we just dump energy on the grid. And they do brute force, literally shutting off wind turbines if they're over-generating and grid cannot not accept that. Then, you don't see it from my from the video, but then all these distributed energy resources are happening behind the substation at the distribution level. So you have solar, you have EVs, you have storage. And what is this? This is neither node nor generation. That's where confusion gets. However, the whole community is used to do very conservative top-down management. They only dispatch generation and match it to load. Anything that is behind the substation is called net load. So whatever load you have minus whatever power you produce locally, they subtract that. And that's what they have to serve. And when you have renewables that are highly variable, that net load varies. And that's something that doesn't work with the timescales they're used to manage it. So the way to deal with that, they actually plan for the highest peak load. So they're super conservatively running this system. These are just giving you some idea of time scales. So when you hear about system operators like California ISO, New England ISO, what they are doing is they're day ahead, literally, based on some information they have historical. They are deciding only on the price of power that power plants are bidding, who are they going to deploy on the grid tomorrow. They don't care, is it coal, is it wind, whatever is the cheapest goes first, and then they keep filling the stack. And they do it a day ahead. And this is called unit commitment. So this is very long-term planning. And then on hourly basis, they monitor, are they serving the load? And they have smaller plans that they pay in advance to be ready to be dispatched. And this process is called economic dispatch. And then they do have ways to keep the grid stable. I don't have time to go into math, but at any point in time on grid, you have to have exact match between power generation and load. Otherwise, things start tripping off. That's just the physics of the grid. You cannot, unless you have storage and you store power somewhere else. But if you're producing it, you have to have exact that balance, and proxy that you have a balance is frequency. So frequency is 60 hertz, and if you have overproduction, frequency goes up, and they monitor that. That's how they see the changes. And if actually have underproduction, they see the frequency going down. And that's why we have these frequency regulation and ancillary services that they ask plants to do. Only feedback control that exists on the grid is something that is done at a large synchronous generators. This is inertial control and governor control. So every synchronous generator has a beautiful decentralized control called droop. They sense if frequency goes up or down, and they spin faster or slower. And that's totally independent and totally decentralized. Then you have a governor response, and then AGC is the only thing that is a centralized entity doing, basically based on deviation of the frequency. They bring some of these power plants to control the frequency. So all you need to know about reliability of grid is this chart, and people somehow forget it. They go into markets and balance and what. But this is this is the frequency across time, and we want to give it 60 hertz in US. In Europe, it's 50 hertz. So if one of the big generators falls out, this is so-called contingency event, you will immediately see frequency going down. And this is in this short few second interval, this is when the droop control, autonomous control works, when each generator senses this change and they start spinning up, and they bring it to this settling frequency, which is below 60 hertz. And this is where automated AGC, that I told you is the only centralized feedback, kicks in at between 20-30 seconds and brings additional power plants to restore the frequency.
So who is they?
System operator, ISOs, RTOs. And what are now the challenges, technical challenges with renewables? So we know how to dispatch generation, but what do we do with this intermittent variable generation that is connected at the distribution level? We used to have pretty good idea what the consumption is, what the load is. Now we have variable net load because we have some of this intermittent distribution generation at the distribution. We built a grid so that we can reroute power in case of certain events, but now we have big power plants like wind plants at the places where they were not initially planned for, so we have congestion. Studies have been done, and renewables penetration is limited to 30% because of lack of capability to reliably and affordably manage its variability. So what does that mean? That means that to go to a higher percentages of renewables, we have actually to start controlling net load. We cannot continue doing this top-down management. We have to control everything that we have on the grid. And what is the problem here? It's complexity. You think of all the little devices that you have at the distribution level. Even if you actually in the lab develop some way of coordination, how are you going to scale this up? How are you going to prove that it works in a real system? Then stuff that I already mentioned, variability and uncertainty in the system comes from different sources. So what our technology needs that we identified are more sensing and more data processing. There's very little measurement done at the distribution level. Some utilities don't even know where the wires are, let alone to monitor what is happening with the voltages or with the frequency. Then also better understanding of forecasting the weather that affects both consumption and the generation. And then engagement of the customers. Communication is an area that is not being standardized or explored extensively enough. I had discussions this morning about that. And then controls, using basically feedback to take care of some of this variability and certainly locally to alleviate this planning and basically decompose problem into smaller chunks. So what we did, and this is part of a ARPA-E process, is before you are actually handed 30-something million to have a program, you have to justify that it's worth investment of the taxpayers' money. So we commissioned GM Energy Management team, and we did study with them. So I worked with them, and we said, what if we actually can dispatch distributed generation in coordination with the bulk power plants? What if we can actually shape the net load, control that consumption and generation at the distribution level, and do a good job in coordinating consumers in central stations? Would that help? You can advocate that some of this is already being done. However, what is being done in very brute force fashion, and consumers don't like it. Demand response these days means you turn something off, and people do not want that. So how can we actually do some of this without actually affecting quality of service to a customer? And the other thing is we have to develop trust with the utilities and system operators that actually these DR devices can help them, that they're not a problem maker but problem solver. So they have to understand what kind of capacity they have on the system and how does that affect overall system performance. So what we wanted to do is, this is a standard process. We wanted first to identify what are possible approaches to addressing this problem, see what would be the impact of them, what are the right architectures of the system, and also define benchmarking. So this study that we did with GE said, okay, we'll use, and they have extensive simulation capabilities of, like, for example, whole eastern connection of the US or western connection, and the same team that did that study that said that 30% is the limit worked with us. So we said, okay, we will assume that actually some of the net load can provide the same service to grid as synchronous generators, that we can provide this inertial response in seconds and govern response in tenths of seconds. And what if we actually have 30% flexibility in load? Could we actually have more renewables on the system? And this was a couple months of studying, playing with the different scenarios. I will tell you two things. You can put as many renewables as you want on the system, you won't use them, so they're not going to be economically viable. So what is showstopper this RU, which stands for Renewable Energy Utilization. So this study that said 30% is limit was because if you go beyond that, utilization would be less than that, and then it wouldn't be economic to put renewables on the system. So we run several scenarios. We have per 50% renewables. Out of that, 15% was distributed solar, 10 was central solar, and 75% was wind. So if we do business as usual, top-down, conservative management, we can do it, but utilization will be about 79%. So not economically justifiable. If we actually provide these inertial and government short responses, then we can bring this usability to more than 90%. And in the whole process, we can save 2.8 quads of BTU, which is a lot of energy. If we actually additionally can shift energy either by storage or by adjusting the load in long time frames, then we can bring utilization even further and save more energy. So this is what was enough to say, okay, this is worth of a program. Let's look what we can do about this. I'm just going to briefly go over this. This is showing you 1 week and what are the load scheduling. At the bottom you have, this is when you hear base load, that's the pink thing, and that's actually nuclear plants that do not move up and down, so you have to deal with them. And they are to some extent source of this inflexibility of the system, because if you look on the right hand side, you see pink and green. That is basically modified load served by pink portion, which is nuclear, and green, which is renewables. And on some, this is very bad week where if something happens, you don't have anything to move. You don't control right now renewables, you cannot move nuclear. And that's why they don't want to go above 30%, because you cannot control the frequency. This shows you what is the generation mix that we ended up with utilization of some of these load modifications. And on the right-hand side, we distill basically periods of time when you need to store energy and when you are releasing it. So you can see because of large number of solar that we have, the red periods are when you have overgeneration, you have to store that excessive energy, and blue is when you have to use it. You don't have enough power in the system. So to summarize the study of a couple months, we actually looked what if we don't have any control and we want to have 50% renewables. Then solution gets very expensive. Transmission upgrades required, for example, for PJM would be at the extent of 14 billion, but there will be lots of curtailment as well. If we do local control in a second and minute time frames, we actually we still may need some transmission and distribution upgrades, but we do bring utilization higher, and this is more economically viable. And then if you do load shifting in hours, we can actually get renewable utilization even higher and make this whole solution more affordable. So this, for a control scientist, is a very good picture because it tells you that control happens. For power electronics people, they love this portion when you show the local control, because that has to be done by use of some power electronics driven devices like solar and storage. And then this is telling, okay, this will create impact. And then what is the right architecture, how to implement this? And this brings it, I mean, this is something that you guys who are working in the systems sciences should look into. If you go to Bay Area, they don't need grid, they will do everything decentralized, local, fine. You go to utilities, they will tell you, no, we are just doing it centralized the way how we are doing it. So they're like two opposite ends of a spectrum. So what we've done, I had a postdoc at the time that was working with me at ARPA-E. So he went and processed publicly available information, and these are depending on 6 different scenarios of what will be the load as we progress to 2040. And then these are some projections for residential and commercial distributed generation. Very low. Their projections are conservative, but nevertheless, it's still low. So then if you add on top of this wind, and then if you do rooftop solar and community solar, like every surface that we can cover with solar, this is where it brings us. And then we had some combined heat and power program that had projections of their own. So if you add all this, it shows you that you can cover about half of the load with the renewable generation. So our conclusion after this was, okay, architecture will be hybrid. Certain things will be done locally, but you will still have to be able to transport power along distances to bring it to consumer. More recently, I think about a year ago, Angel did another study where they analyzed the maximum possible installation of urban solar. And if you look into this study, then it looks like we can actually cover all the load with the renewables, which my postdoc, and I let him do that, he wants to interpret that this means this is how much we're losing. This is, opportunity lost. So this was telling you there is impact. We have to look into right architectures. I described to some extent approaches, and then we sat down and distilled it so that we can have people who are very familiar with power systems, but also bring into field people from controls, from modeling, from data analytics side. And we said, look, we want to enable more than 50% renewables on the system. We want to keep the same efficiency and reliability, so no black rollouts, nothing. Guarantee level of service to consumers, and also guarantee level of service to system operators. What we've done is we decided to formulate this in a fashion that is actually easy for adoption. And I mentioned before that there are these reserves, so small generator units that are used for so-called ancillary services when you have discrepancies in frequency that are being brought on. So we said, and we also went in and analyzed all the historic data that is publicly available for all system operators, Cal ISO, New York ISO. And they call these reserves in different names. So we came up with these three different categories. We call them synthetic frequency reserve, regulating and ramping reserve. And the only thing, if you're a controls person, that it actually distinguishes it from each other is what latency you're allowing, how much they have to react, how fast they have to ramp up, and for how long they have to sustain power. So it may look simpler than it is, but actually this generated lots of talk in the industry, because apparently lots of people in traditional power systems do not utilize power scale separation, and that's where this complexity comes as a problem for them, because they want to control it all at the same time, and that is too complex, and it can't be done. And the other thing is that I'll go through each one of these categories. Each one of them is like a Trojan horse. So we had a set of possible solutions that we are expecting to come in proposals. We're not looking for them, but we were speculating. And I'll go through each one of these categories. But basically, first category is calling for autonomous response. You don't have time to talk to anybody to do anything. You have to act as autonomous as you can. Second one is allowing for coordination. The third one has to be in a hybrid architecture, managed from the top. So when I talk to people, what do we really want to control in this program? As opposed to controlling bulk generation, renewable, non-renewable, some industrial load that is being done, we want to control net load, net load or grid edge are the same. So it's literally called edge because it's on the edge of the grid. So we want to use these different devices to, in aggregate form, provide low-cost ancillary services at different time scales. If you think what this is doing, any engineering system can be beautifully engineered by domain experts. What they do is they usually leave a very big safety margin to make sure that things work. Where feedback and control help, any application look is that you actually control dynamics locally, and then you have a luxury of getting closer to the safety margin, because with the feedback, you'll make sure that you don't cross it. So this is basically saying, okay, let's use these devices to lower the safety margin, require less reserves, and make the whole system cheaper, because these devices we already have attached to the grid. So first, and if you think of these these three categories, they can be bin into two categories. First one is synthetic inertial response. So the fact that grid is stable is due to the fact that big synchronous generators have a lot of inertia. So even if there is an event in a system, that slope of that frequency response that I show you depends on the masses of all the synchronous generators. As we change the mix of power generation, less synchronous, big, bulky synchronous generators, there is no physical inertia in the system, so this frequency changes fast. And they're already seeing it in Texas, because Texas has 40% of wind on the system. So this is basically trying to create response from loads from storage that mimics synchronous generators, that you react to this local change in the frequency in autonomous fashion. And the challenge there technically is, what if you have lots of these devices? How can you guarantee that this will actually have effect on the system? And how do you tune all these changes? To make sure that at least we make a dent, we ask teams to actually do hardware in the loop validation with 100 actual devices at power. So I'm not talking Raspberry Pis, I'm talking 100 EV chargers, smart appliances, whatnot. And then to show that it scales up, do it in simulation. Next two categories are different. They're basically asking for coordination of load generation and storage so that you change the shape of that net load. So at any point in time, you have exact match between generation and the consumption. And here we are exploring, sorry, I forgot to say one thing. At the top right hand corner of each category, you're showing the lead organizations for teams that are getting funding. So these teams are basically trying to figure out how to coordinate a large number of heterogeneous energy resources, and also understand, because here you have to do some coordination, but what are the right architectures of communication, of control, who has to talk to whom, what is the overhead if we actually put this in a system, how much do we have to pay for the communication, is this worth it? And these are all things that have to be considered. Again, validation with 100 actual devices and large simulation scale up. And the third category is doing the same as second, except it's doing it over hours. And why do we need this? This is something that I don't know how many of you are familiar with the duck curve. Have you heard of a duck curve in California? So in California, you have lots of solar, and between, I think, 4 and 7 p.m., they need 13,000 megawatts of power, because sun goes down and everybody gets home and wants to do different things. And there's this steep ramp that they have all of a sudden serve, and that's called duck curve. So this is trying to address that to some extent, that you flatten that ramp, because you don't have to exactly do everything at 6 p.m. or 7 p.m. whenever you get home. And this is where teams are actually mainly working with large populations of big loads, buildings, portfolios of buildings, microgrid, stuff like that.
So you have at a high level control over how people and when people consume electricity, or at least a building?
No, it's different. I can show you 3 teams. I don't have time. So these are the teams that got funding. So these are all organizations that are getting funds. Each one, and it shows which categories they're addressing. Some of them are just doing 1, some decide to do 2. The PNL is ambitious. They're doing 3 with United Technologies Research Center, and they're using TRC's building testbed. So as I said, I don't have time to go into each one of these. This is a slide that is showing you what's the interest that we are driving in the industry. These are members of advisory boards, because for our teams, we are asking them to actually go and talk to their end customer or potential adopter of the technology. Depends on, if it's academic team, usually we ask them to get people from, let's say, New England ISO or utility. If it's GE, then we want cities or utilities to be. So you can see that we have who's who in power systems. And what is interesting is that when we started, lots of people were hiding in the bushes, and as we progress and make presentations and teams make presentations, they're coming out of bushes and say, yes, we have this problem. So we even have people like Nest and Google, and used to be Solar City, now Tesla, Schneider. So they're all overseeing what is going, and providing their input too, because teams have at least one annual meeting with the advisory board, and we listen closely to what they're saying. So I'll give you this slide, and then I'll give you more about the projects. So what are the architectures emerging? And they're very aligned with what is going on in industry. So system operators are the guys who are running this day ahead and economic dispatch that is daily and hourly basis. Those are ISOs, like California. And some of them are allowing aggregators of DRs to actually participate in wholesale markets. So you can bid the same way as a big power plant in the day ahead market if you can guarantee them that you can move load up and down up to a certain amount. These are all regulated. This is what California is doing, and this is happening now. When we started the program, it wasn't happening. It just started last year. New York is trying to deal with the complexity by replicating independent system operator transmission level at the distribution. So say, okay, you guys deal with all these aggregators, and then we'll talk just to distribution system operator. This is DSO. What some of us dare to think, and I don't know if anybody from utility is listening to me, they don't like this third option, which I think is the future, that power system will be probably a superset of microgrids. And when I talk about microgrids, I talk more about so-called soft microgrids, so portions of distribution that are serving the load. So you will serve load as much as you can with local generation, and you will use grid as a backup. The way how we will pay for that is another problem, because we have to, and there are long debates about this going on in industry. Utilities are on board with this. They know that this is coming. They just don't know how to do a smooth transition, because the business model that they have is they invest in infrastructure, and you and I pay fees next 30 years to make them make money on their investment. Now that they don't have anything to build, we build everything locally. They're just like internet provider. They provide these existing power lines. Where does money come from? So we have to work with them to figure out what kind of services. And everybody's talking about basically utility becoming a service provider. And you will have different tiers of services, depends on how much reliability you want. Lots of aspects coming to this, risk quantification, and things like that can be learned from other industries. And few projects that because you won't have time to ask many questions. This is the most traditional project that I have, where Arizona State University is working with Nexent, which is a company that has their software for energy management in lots of utilities, and PJM, which is a system operator. PJM operates grid in Pennsylvania, New Jersey, and Maryland. So what they're doing is they're developing a tool, advisory tool for the operators, because all these things they had and economic dispatch that are done as a planning, they're done by use of software, but they are verified by people. And even what they call real-time markets, 5-minute markets, are again done through human operators. So what we are trying to do is actually use some of the more advanced techniques, like, I don't know, in broad terms, machine learning, but basically trying to predict generation load based on the weather patterns and quantify this uncertainty flexibility and take that into day ahead and hour ahead planning, and have them, accept that you actually have more levers, not just dispatching the power generation, but you can actually tell people to bring load down, or you can count maybe more on local generation so you don't have to overstress the network. And initially, this is based all on stochastic optimal power flow. So it's basically, right now in most system operators run mixed integer based optimization, and there is a monopoly on software. There are like basically 3 large OEMs who provide this software, and they don't want to move. However, because of all these issues that are arising, stochastic OPF is becoming considered by more of them. So when we started, everybody was proclaiming us semi-crazy. Now they all talk to this team. California ISO, MISO actually wants to get on board of the team, so we are working on adding them officially to the team. And so they're looking only in long-term shifting. This is a very entrepreneurial team. They already launched a company called Packetized Energy, and they have some initial seed funding. So they are transitioning technology that you develop for communication networks. How do you actually schedule packets in a network? So what they are doing is they're integrating transmission and distribution, but at a very low level. You as a user say, okay, I need this much energy at this time frame. And for example, you need to charge your car for 2 hours, but you don't care when it is, as long as it's charged at 6 a.m. when you're up. And they're using randomized algorithms basically to shape that load, to assign, to match requests from the users with some of the signals that they're getting from a centralized entity. So there is some decentralization, but again, you have to respond to price signals. They are lucky because they're in Vermont, and they have on a team both system operator in Vermont, Velco, and they have Green Mountain Power, which is one of the most advanced distribution utilities. So they're actually already testing these things so they developed a little device that you put on a water heater, and they're expanding it also to EV chargers, and you can actually coordinate charging. And water heaters are very cheap battery, if you think about them, and lots of people are using them. And then Enel is doing something that is more out there, distributed optimization based control of the grid that is built on stuff that was going out of Caltech. I don't know for those of you who follow Stephen Lowe's work, but extending it and trying to use some physics of the network that helps you actually get faster to convergence of the solution. And these guys are testing it in NREL. So NREL is a good government lab to partner with because they have one of the most advanced energy system integration facilities that third parties can use. I actually twisted their arms, so they had to put even more things because of me. So I was counting. I wanted those 100 different devices. So they have 2 mock-up houses with smart appliances. They have different batteries, EV chargers, and they are trying it now in a small microgrid in Sonoma Valley. And if they're successful, then they will be going to utility in Aspen, all the nice locations, and try there. This is another driver that we are seeing. There are lots of communities who really care about this, and they want to take initiative when it comes to greening the environment and technology. And they're volunteering in terms of letting their facilities be used for the testing purposes for advancement of technology. So going forward, we continue to engage industry, address technology needs, demonstrate capabilities. I think demonstration is critical because I tell people I can simulate anything. But when you transition that into field, then things happen. And then I'll use the opportunity to let you know that we are continuously hiring. The only hard requirement is you have to be US citizen. So we are hiring program directors, tech-to-market advisors, and fellows. Fellows are basically postdocs. So after your graduation, you get to spend 2 years in ARPA-E, and it's, I think, fantastic opportunity to learn how DOE works. So you get actually more freedom than program directors. So you help identify certain spaces where you want us to focus or work very closely with the program director. So the postdoc that I mentioned, his name is Michael Kane. He's assistant professor in Northeastern right now, and he just started there last fall. Okay, thank you. I was trying to cover the room, but I don't know how to move and stay on camera.
Yeah, that sounds good. We'll improve. We have a few minutes for questions, so if anyone has any questions?
Yes.
You mentioned that to at least control this loading, you're on the edge, but like, what are the mechanisms other than what you did mention was like they request for something to be done and then you can move that scheduling? How would you actually control the load at the distributor plant with face?
If I'm understanding your question, first of all, this is where people get confused, and I didn't have time to go into that. You usually have entity that aggregates all different devices. So there is one point of contact between either utility or system operator, depending on what's the architecture. So they have these signals that they send. I want you to move, that you have to follow. I want you to move this much, and it's literally trajectory tracking. And you, as an aggregator, have to figure out how to turn that signal, how to track that trajectory with capacity they have under you. So lots of people are doing, for example, model predictive control to do that. Some are doing this stochastic randomized based algorithms. Some are doing robust control. So I don't know if, so it's almost acting like and there are multiple terms that we'll use virtual power plants. So in aggregate, let's say this is a neighborhood and all these houses can go up and down. You can, for example, if you have solar, you can actually consume less because you can perhaps use your local. Or if you had overgeneration stored in the battery, you can actually put some power back into grid. So you just have to follow this trajectory, literally, and it can go both up and down. That's what is hard to understand, because usually what we do now, we just turn off load, just disconnect load. Okay. Correct. So that's what's called demand response. And that's why I don't use that word, because it doesn't feel good to people. If you lived in Minneapolis, for example, as I did, utility has direct control of your AC. So they have few very hot days during summer when they have brownouts, that they call, and they will literally turn off your AC for a couple hours. People don't like that. What we want to do is move the temperature of your thermostat, and you won't notice. That's what so this is the knowledge I acquired when I was doing building control at UTRC. We had lots of energy efficient building control, and we were doing very fancy model predictive control where we were using weather forecast, load forecast to save the energy. And when you look at what is the fancy control doing, it's basically moving thermostat set points a degree up and down because you put constraint on it. So what we envision that some of these technologies, let's say you have a Nest, you will say, okay, I'm cool if you keep my room between 67 and 72. You're fine with that, and then your aggregator will have this, and they have like thousands of these, and then they know how much they can move. So they will control your thermostat and because buildings are, this is another thing that I have, 40% of energy in the US is used by buildings. And that's why what inspired me to start NOS, because I was working on the buildings and realized how much flexibility we have in that. And we are putting expensive installation of electrochemical storage or thermal storage, as opposed to trying to figure out how much of this we can do with a flexible load and how much storage we need. And this is something that we hope to come out of a program. What's the ratio of the two?
You mentioned that DERs has to be aggregated first and then participated in the market. So I just wonder, how is the revenue allocated between among these DERs?
I did not say that, because not everything in US is under market. And we do have teams, like one of the teams is led by National Rural Electric Cooperatives. Actually 70% of land in US is under co-ops. Co-ops are not investor-owned utilities, and they are cities, they're municipality owned, and then they serve so they don't care about profit, that they just want to make sure that their users have power. And they are actually more willing to try some of these technologies. The other thing that is a fact, they also are not under regulations of NERC, so they don't have penalties. So to defend investor-owned utilities that are under market, if they cause a failure in the system, they have big penalties. So that's why they're conservative. And in terms of distribution of the revenue, there are different models. So there are some startups in Bay Area that are, for example, you subscribe to them, they will give you flat, I'm throwing numbers at you, I don't know if there is like $30 a month if you let them do this with your thermostat, and it's up to them to figure out how they participate in market and make themselves profitable. There are some that actually want to pay per mileage, not just instant. You know, there are all sorts of, and then you have also for some other assets like big commercial buildings, people are very interested because apparently people who own these commercial buildings, lots of them are using energy when they really don't need to use energy. So this could be an additional revenue stream for them when you run them in more energy efficient way, but also participate in some of these markets. And those are some of the things that we're exploring. GE is doing that with Mbala networks. And it's very different from where you are. You know, how do you participate in the market? The only real market right now going on is in California ISO. Yeah.
Thank you for the answer. I have 2 more questions.
Sure, go ahead.
The second one is, what's the problem? Why DRs cannot participate in the market individually? That's the first one. The second one, is that possible for the DRs formulate, for example, called like energy community, and they share actual power or actual thermal energy together?
Okay. First answer is they can't cannot participate individually because there is no way for the system operators to manage that. It becomes too complex. And not only that, but if you read instructions for the California ISO market, markets are run by optimization software. And it's mixed integer. And then for the whole California ISO, I don't know how many, maybe some of you who do power systems know how many, what they call price nodes have. So initially they will tell you that DRs can participate in the market if you're connected physically in the area of this price node, and you had to have, I think, 0.5 megawatt of assets of the same kind. You could have it at different price nodes because this is literally how their software, optimization software works. Or if you have heterogeneous DRs, they have to be connected to one price node. They apparently changed that, but it all boils down to limitation of optimization software. And if you talk to them, they won't say that publicly. And do I have utility rights on the phone or not? Cut the phone.
Stop the video now.
They will tell you, if you make these DRs in aggregate behave as a generator, we are good. Because the parameters of a device in their software literally are just parameters of a generator. They don't have a way to specify big storage or big renewable power plant. And that's going to change, but this is the... And what was your second question? Was
is that possible for the DRs formulate, like for example, an energy community, and then share the actual power?
Well, that's what that is what coordination is all about. You know, so that's what people are doing already. It is possible, but you have to take into constraints of the physical network. And I didn't have time to go into this. All these guys have to do this, but at any point in time, because at the distribution level, there are very strict regulations how you keep the voltage at certain, and that's not, you know, people think that you just connect devices and miraculously it works, but they affect each other and then voltage goes up and down, and that's not, some utilities actually don't have to put measuring devices on distribution so that we don't see these deviations of voltage, because then they will be paying penalties, you know, or having to do something about it. So they are exchanging it, and you can do it at the level of community. It depends on the topology of the power lines, and most of power distribution US radial network. So literally there is one point of contact, and then you have power lines going in radial fashion. So it's very hard. So if you're on the same feeder, you can exchange. But if you are, so that's, some people are doing what's called looping. They're connecting ends of feeders to connect a loop where you can do some exchange. In the big cities, you have mesh network. So that's why New York is doing lots of things, because they have mesh network, and they can actually, they have more paths to do. So I have, in addition to these, I have several other projects that came through open solicitation. So one of my teams is actually looking into this dynamic topology. If you have these smart switches, and how can you reroute power within the microgrid to cover critical load, for example.
What is the corresponding price mechanism among sharing?
Sorry, I didn't...
Besides the price of the actual power or thermal energy share? So no cost, just to share with each other.
You're asking, okay, we haven't figured out the retail market at the distribution level. Now, what you're asking is what people who think blockchain is a holy grail that will solve it all are saying we'll do it with blockchain. And you have a gazillion of startups looking into that, but blockchain is basically a distributed ledger that is letting you do distributed transactions, but then there are no constraints of the physical system built in it. So I can fictitiously exchange power with you, but can I really send you that power? I do not know, because I don't know if there is enough capacity on the power line to do it.
Great, thank you.
Do we have time?
I guess we don't, but let's thank our speaker and can ask your questions. Thank you very much for doing this.